I'm picking up the topic that was just explained, but really scaling it up. So we saw a lot of interesting applications of additive manufacturing today. Additive manufacturing is a really very broad term. And usually the question is for architects, okay, if I want to print my building, we saw the concrete building before, we run into all kinds of issues in terms of time versus scale versus detail that I can print. Yeah? And I think what we have here is an additive manufacturing technique which has a lot of benefits of additive. Wasteless, you only add the material where you need it actually, and it brings also a new paradigm into industry where you can vary your parts and individualized production of pieces. And I think that's very interesting to explore on multiple scales, but on architecture especially. Just very briefly, so I'm a little bit between industry and academia. We just briefly started our company, bringing that into application. Before I was actually developing these techniques for 6 years at the University of Stuttgart, and since the last year I was teaching as a guest professor for emerging technologies here at the TU in Munich. So what we've done in the last years is really go from the very basic research all the way to implementing that on larger scale. And that's very interesting and unusual for an academic setting, where we really looked together with biologists into lightweight structures in nature, and then see how that can actually be implemented on a much larger scale on architecture. So there's a really big jump in scale, and that puts a big question mark on the technology that you then have to implement these kind of structures. Why do we look into beetle shells or into something like that is oddly shaped? Because it's a very efficient and material efficient structure, and that has a lot of interesting functions integrated as well. Those are some benefits that architecture could really use. So all the building technology that we see here with the piping and the exhaust and everything got much better over the last years. So buildings use really less energy than they used to be. The problem is we haven't changed anything with the hardware. Yeah? All the beams, all the steel is still the same, and it's consuming vast amount of resources. We have a big growing cities, increased building going on. So basically what we need to do is we need to drastically reduce the amount of materials that we use in construction. So that's how nature does it. They use fiber-based materials. So every load-bearing structure in nature is a fibrous material. So a plant is a fibrous material. We also fibrous material. Collagen fibers arranged in different ways to make it very material efficient, to be structurally integrated, and at the same time have all those functions as well. So how do we translate that into technology is really a big question. So this Futuro house is actually sitting in front of the Pinacothek as well here. So it's a really great example of early applications of plastics in architecture. And it's to a certain degree also additive manufacturing. You layer and layer these mats of glass fiber into a mold. The problem is that you're very stuck in the old fabrication paradigm where you really build up sheet by sheet, and you have industrial paradigm of fabrication. You repeat the same part over and over again. What we're really looking at is a different change in paradigm, where in a much more biological paradigm, where each piece is differentiated, locally adapted, and the question is now, how can we adapt the technology to build fiber composite pieces to enable this kind of new way of designing and making parts in architecture? So basically transferring a biological fiber lightweight structure into technical fiber lightweight structure that can be used in architecture. And we do that with technologies we have at hand nowadays, which is not only, we talk a lot of fabrication today, how you use the printer to do things, but there's a really long series of integrated computational design and simulation steps that are not the sequential steps of designing and making, but it's really integrated. So basically, we know how the robot can operate, and that informs our design from the very beginning. And that allows us actually to have this in 2012, the first prototype we made. The robot winds each string, if you want to call it like that, bundle of fibers individually. The interesting part is here, we only add the material where it's required. We only have a very minimal scaffold underneath, and the form is emerging through the process. So all the curved areas in between are really emerging from those fibers interacting in space and adding up to the final piece in the end. The interesting part now is that we scale that up to architecture scale and see how we could really build our material efficient constructions with this. So that's sounds like a very technical task, but in the end you see that we open up a novel design and construction repertoire with that at the same time, which is really interesting from an architectural perspective, where it's always about technology and design at the same time, and it's not really separable from each other. The interesting opportunity we had here is going through a whole iterations of these one-to-one scale demonstrators, which is really important because you test the technology on that scale, you see the problems, you raise questions for the follow-up project. And those parts that we made are only vehicles, actually, in an academic sense, to develop the tools that we need, the methods. Yeah? So generating a shape rather than drawing it, we thought before, all the parameters that you can change on such a design, and then even going a level deeper where you then define how the robot needs to apply those materials step by step. So also designing a big winding frame like that seems like a technical task, but when we did that in an integrative design way, every decision you make on that side affects later what you can do in a design side or as an architect. So it's a very interesting way how technology serves as a design driver in this sense. So what we have here is to do a robot setup, and the fibers in between are just forming this shape through the robot code. So this curve is emerging through the instructions we give to the robot, and is not like inscribed in some kind of a formwork or mold. It's only the pins on the top right which really are defined in space. The rest is emerging through the right sequence of fibers coming together. And that actually allows us to build each part in a different geometry and each part with a different fiber layer. That can be assembled in a very lightweight manner and bring together this very filigree construction with it. It's at the same time super robust. That's the interesting piece here, that, for example, here was the World Soccer Cup, there was a big screen next to it, all seats were taken, so people started lining up. We had 25 people sitting on top of this thing, which looks like if it is just made of string, but it's actually super strong. So that's the interesting part, that we at this point realize this is a construction system that we can take to a different level. And the interesting piece here is, if we look at the shadows, if we look at the level of detail that those fibers exhibit, it's really also a different way of using the material. Because we developed the methodology in a bottom-up exploration and really see, okay, when we have this type of material and technology, how do we need to build with that? Yeah? We don't need to fit into an already predefined construction line and need to replace a certain step there, but we can think it all from the bottom up, and that enables us here to build fiber composite structures that also look like fiber composite structures, and it's not just a polished piece. Yeah? Like you have, if you have your car hood made from carbon fiber, yeah, it basically still is like a varnish cover on a lightweight piece. Yeah? And here really it's how a fiber really wants to articulate itself. And we use that for a series of interesting projects. It's lightweight, it's modular. We used it for fair stands, where people need to carry these things around every day. It needs to be light, it needs to be expressive. And I think that's interesting to see the process a little bit. So the fiber is dry, it's impregnated with the matrix, it's coming from the spool, and the robot places this on this steel frame. Then the whole thing is later hardened, the steel frame is taken out, and then only the fiber itself becomes as strong as the steel was before. So that allows us to build these pieces, which all have the individual fiber layer. So each of them was calculated to fit in a specific point in the structure and only used a material that's really locally required to reinforce this kind of structure. We also showcase the portability of the technology here. This is basically our 3D printing cell, if you want to call it like that, which can build such a roof. And I think here, that's the last project I did at the university environment. We really brought it to a scale where we had really nice integrated construction details built into the parts themselves. So that's also similar to additive in terms of printing, where you can have integrated connection details and functional features integrated in the piece. That's something that we can do with our robotic filament winding process as well. For example, attachment pins for the roof cladding. And the whole thing illuminates quite nicely at night and was used for a trading party with we know was there. Quite a fancy party. And basically based on this whole line of academic explorations, we were approached by a lot of people, and applications start our company where we actually implement those processes. So again, the fiber comes from a spool, goes to this minimal frame, is wound on top. The interesting thing is that the process works with a whole kind of set of materials, also similar to printing, natural fiber, glass fiber, super high performance carbon fiber, whatever is the best application, and make these open mesh structures. Basically all the material, you don't see here's the material you need, and we can integrate nice gradients, denser areas, lighter areas, for either design purposes or for structural reasons. So I just quickly want to go through a few things because it's interesting how you can apply that on larger scale. So that's a 30-meter span structure that's going to be in Heilbronn in April 2019, where we build up to 6-meter long carbon fiber beams. They will hopefully look like that. Then we're developing our methods further, so we keep in touch with academia and develop different fiber layouts together with the structural department in the University of Stuttgart, and then see how a carbon fiber beam under a certain load condition would need to look like in the end. And facades are interesting. For example, here where we should explore a certain textile character, which the process has a very textile character, and it can be expressed in the facade in a certain way in different studies. Furniture with an architecture office from London, we looked into furniture prototypes. And then when I was teaching here in Munich, we were working with two professors who looked into urban microclimate, and we wanted to see how can this not only be a very material efficient modular lighting structure, but how can we also make it beneficial for the urban climate when it's outdoor, and had a certain plant system integrated in our modular structure, where it was also prefabricated, wind on the frame is taken out with the piece, and this very interesting material character where light at night the whole thing is illuminated and we set it up in Frankfurt at the Illuminado Festival. Furniture, so all the way down in scale, here we tested some new materials, and that was shown as there. So basically running from early academic explorations all the way to now implementing it in industry, and I think that's a really interesting additive manufacturing